Okay, so now we're going to do the inductive load. This one we got to be real careful on. Once again, AC source, there's the inductor. We're going to have some voltage across the inductor. We know that the voltage across the inductor, by the loop rule argument that we used on the resistive load and on the capacitive load, we know that that voltage across the inductor has to be equal to some maximum amount of voltage, capital VL, multiplied by the sine of omega dt. Okay, so we know that that has to be true. But we also know that the EMF inside of the inductor is going to be based on the time derivative of the current with a minus sign. Yes, this is going to suck. So this is going to be the EMF inside the inductor is minus the inductance di dt. Okay, minus L di dt. So we take the time derivative of the current, that's going to give us the EMF inside of the inductor. So now I'm going to replace those two guys. I'm going to not worry about the minus sign right now. And I'm going to have that the voltage across the inductor is equal to L di, the current across the inductor dt. So notice what's happening here. This is going to turn into a little bit of a mess, but I promise it's going to be okay. The voltage in the inductor is equal to the inductance times the time derivative of the current in the inductor. Yeah, okay. But that still needs to hold true up here, that I still have to have the sine function up there. So now I'm going to combine these two ideas. And now what I'm going to have is I'm going to have dIL, so that's the time derivative of the current inside the inductor, is equal to the maximum amount of voltage across the inductor divided by the inductance times the sine of omega dt. Okay? So look what I did here. I divided the L over to the other side, and I replaced this VL with this right here, the VL sine of omega dt. So now I've got this guy. So if I want to figure out the current, it should be pretty obvious what I'm going to do. I'm going to put the dt over here, and then I'm going to integrate both sides of the equation. So in order to figure this out, to figure out the current across the inductor, I need to integrate the current across the inductor. Okay, so I'm going to integrate this di dl. Okay, so the dt came over to this side, and now what that's going to give me is the integral of VL over L. This is a capital VL standing in for the amplitude of the voltage, the sine of omega dt. dt. Okay, that was a lot. The dt came to the other side. I need to integrate this sucker in order to figure out the total current. So that's me integrating it, and that means I have to integrate this side with respect to dt. When you integrate the sine function, you're going to end up getting a little bit of a mess here, and we're going to get that the current across the inductor is equal to minus VL, capital VL, over omega dl times the cosine of omega dt. Okay? So that's what we got right here. We integrated the cosine function. We have to have the omega dl in order to cancel out the omega d that's going to come out from the integration. Now once again, we want to make this look like a resistor. So we're going to introduce something called an inductive reactance. So chi L, the inductive reactance, is going to be equal to omega d times L. Omega d times L. This is inductive reactance. That's our inductive reactance. Again, we want this to look similar to a resistor. Pause. Make sure you guys have got this in your notes. Okay. We have a slight problem. From the last whiteboard, we had a cosine function with a minus sign in front of it. So we have minus the cosine of omega dt, but we need it to look like a sine function, because we know that the current is based off of a sine function. Again, that's the entire basis for what we've been doing right here with alternate currents. So omega dt minus 90 degrees. So notice that our phase constant for the current is going to be a little different. Our phase constant is going to be a little different. We know that the current inside of the inductor must adhere to the sine of omega dt minus phi. Only now, in order to transform the minus cosine from the previous step into the sine function, we're going to have IL is equal to capital VL over chi L, the reactance, the inductive reactance, multiplied by the sine of omega dt minus 90. So what this means is that the phase constant for the inductive load, inductive load is positive 90 degrees. So there was no phase constant for the resistive load. For the capacitive load, the phase constant was minus 90, and for the inductive load, the phase constant is positive 90. In the last video for this stuff, I'm going to tell you what all that means. Again, please look at the book for those sine and cosine functions, and you should understand what I'm going to do next.